Hi everyone, I'm Vikram and I'm going to present our CVPR paper for attribute classification through latent space debiasing. This is joint work with Sunnie and Olga Russakovsky. In current datasets, certain attributes like gender tend to be correlated with certain tasks like cooking or coding. Now let's say we want to train a hat classifier. Suppose wearing hats is correlated with gender. Then this classifier might pick up on gender cues rather than hat cues. Or, similarly, suppose wearing hats is correlated with wearing glasses, as shown here. This classifier might only recognize hats in the presence of glasses. What we want, ideally, is a dataset wherein these two attributes are independent. One possibility is to collect a dataset that's actually balanced, as was done in the pilot Parliament's benchmark. Here, Wilhelmini and Gebru collected a dataset that was roughly balanced by both gender as well as skin type. However, since the real world is inherently biased, this might not always be possible. A possible workaround is to use GANs to create a synthetic dataset instead, and augment our real images with these synthetic images. As a quick overview, here's how we can use GANs to augment our data. We can sample random vectors z in the latent space and use a generator to get an image for each latent vector. We can then hallucinate labels for these synthetic images using a model trained on just the real images. We can then train an attribute classifier on both the real as well as the synthetic images. An interesting observation made by Danton et al. And Shen et al. Was that the latent space of a GAN is quite structured, and in fact, most semantic attributes are approximately linearly separable in the latent space. This is our first idea. Using a linear SVM classifier, we can learn the hyperplane for glasses, as shown in the image. Now, given a latent vector z, we can project it onto the hyperplane, thereby theoretically removing any visual signal obtained by glasses. However, it's unclear if this actually implies that the predictor attribute is hidden. The second idea is to use pairs of images instead. After learning the glasses hyperplane, we can then compute a vector z prime that flips the glasses core. This allows us to compute pairs of images, one with glasses and one without. The issue with this, however, is that we have no control on whether or not the image generated from z prime has a hat. In fact, naively perturbing latent vectors in this way can maintain biases. For example, when adding glasses, we can also add a hat, as shown here. Since we want to control both the hat attribute as well as the glasses attribute, we now compute hyperplanes for both glasses and hats. Given these hyperplanes, we can now compute a hat score and a glasses score for every latent vector z. We can then compute a corresponding z prime that has a negative of the glasses score but the same hat score. The intuition here is that both z and z prime are either wearing hats or not wearing hats, and one of them is wearing glasses. Computing our balanced synthetic dataset in this way has many advantages. The first one is that our method can use a single GAN to decorrelate multiple target predictor attribute pairs. Previous works here required one GAN per attribute pair. This method also preserves the intraclass variation of the attribute. Consider an attribute like smiling. This attribute ranges from not smiling to partially smiling to smiling. Since the z's are chosen at random, a similar distribution exists in the synthetic dataset. The final advantage is that the samples are generated to maintain independence between the target and the predictor attributes. I'm now going to pass it on to Sunnie to talk about the experimental setup and our results.
Hi everyone, I'm Sunnie and I'll present our experimental results. The goal of our experiments is to understand how a visual attribute classifier performs when it's trained with a balanced synthetic dataset created with our augmentation method. To do so, we train classifiers for 26 attributes in the CelebA dataset and measure how much gender bias each classifier has. Here, the baseline refers to classifiers trained on the original CelebA training set, and ours refers to classifiers trained on both the original dataset and our balanced synthetic dataset. And we evaluate the classifiers with average precision and 3 fairness metrics: difference in equality of opportunity, which is the absolute difference in the false negative rates between the protected attribute groups; bias amplification, that measures the amount of increased correlation between the target and protected attributes in the model's prediction; and finally, the KL divergence between the protected attribute groups' score distributions. First, we compare ours with the baseline. The numbers in the table are averages over all attributes, and error bars are 95% confidence intervals estimated through bootstrapping. We find that ours, trained on both the original and the balanced synthetic dataset, has slightly lower average precision than the baseline model, but has less gender bias, according to the 3 fairness metrics. Further, we'd like to highlight that our performance gains are not from an increased number of samples used to train ours. When we tried training our classifier on the original dataset plus naively sampled images from the trained GAN, the classifier performed worse on all fairness metrics in comparison to both ours and the baseline. Next, we compare our augmentation method to recent prior work. The first method we compare to is fairness GAN, which is a GAN trained with an additional loss function to achieve either demographic parity or equality of opportunity when data points are sampled randomly. The fairness GAN authors train a classifier for the attractive attribute on just the generated data, and then measure gender bias with false positive rate, false negative rate, and error rate. To compare with our method, we also train a classifier for the attractive attribute just on our balanced synthetic dataset and measure the same statistics. We find that ours performs better on most metrics, even though our method only uses a single GAN to augment all attribute pairs, which is in contrast to fairness GAN, which requires training a new GAN for each target and protected attribute pair. Next, we compare our method to several bias mitigation strategies studied in the recent work by Wang and others. We first compare our method to their weighted training method that reweights samples such that the different protected attribute groups have equal weight. And secondly, their adversarial training method that uses a minimax objective to maximize the classifier's performance while minimizing an adversary's ability to predict the protected attribute from their learned features. We find that while the weighted model overall performs well on the fairness metrics, it has a strongly negative bias amplification, indicating that bias is now in the opposite direction, and a low average precision, suggesting that it might be making incorrect predictions to reduce bias. As for adversarial training, ours yield better performance overall, with lower difference in equality of opportunity and lower bias amplification. Finally, we compare to Wang and others' best performing domain-independent training method, where they learned separate classifiers for each protected attribute group and combined them to leverage any shared information. Here, we group the attributes into those with low to moderate skew and those with high skew, where skew indicates the proportion of positive target attribute images the dominant protected attribute group occupies. For example, if 90% of smiling images are those of women, the skew is 0.9 and considered very high. We find that ours performs better for attributes with low to moderate skew, whereas domain-independent training performs better for attributes with high skew. In summary, we introduced a GAN-based data augmentation method for training fairer attribute classifiers, when correlations between the target attribute and the protected attribute may lead classifiers to learn spurious correlations. And our findings show the promise of augmenting data in the GAN latent space. However, one limitation of our approach is that it currently can only decorrelate 2 or 3 attributes at a time. Further, it's possible that while doing this decorrelation, we're adding bias along another attribute. For future work, this is something that we can try to measure and eliminate. As a more long-term goal, we'd like to extend our method to reduce biases in more complex images, such as scenes represented in the COCO dataset. If you'd like to learn more about our work, here are a few links where you can find information. Thank you.